Okay, so welcome back after this 5 minutes break. Our next speaker will be Gabriele Rembado. He's currently at the Hausdorff Center for Mathematics in Bonn, and he will talk about quantization of moduli spaces of meromorphic connections and relations to irregular conformal blocks. So Gabri, please go ahead.
So thank you very much to all the organizers for, this wonderful, event. And also then for inviting me. It's a pleasure always to keep in touch with the Swiss community. The best quantum community I know. And so apologies for being almost late and not being able to join a lot before. It's a busy period, but I will be here then starting from 6 for the question session and so on. I will try to set this up and so it will be better. Right, so since it's 45 minutes talk and since this is supposed to be for young researchers, I didn't think of like displaying, showcasing results and papers and big stuff. I thought I'd try to speak about something more elementary and actually only leaving all the time that I have left after this to talk about the new work. So basically one paper joined with Giovanni. Giovanni Felder, which, so maybe I will try to approach at the end, while the core of this talk will be about, as you see, what I write here, simple pose and KZ, so logarithmic connections with simple pose on the sphere, and the Knizh's homological equation. Or the Knizh's homological connection. So I will try to somehow recall of this and give some background and possibly some viewpoint that's not so known to people, which is about the quantization of an isomonodromy connection briefly. And then again, as I said, all the rest is going to be a blackboard or whiteboard talk in which I give a few ideas about this generalization. But again, that's not the main aim. We can also have more of that during the discussion. Okay. So I have the chat here if you want to ask questions there. Otherwise, yeah, make some noise. I will try and answer. Okay, so we start from 1. Let's have some setup. So please consider 2 integers m and n positive, and then we take the group GLM, invertible matrices, and then it's Lie algebra. I want to consider connections on vector bundles over the sphere. So let us call sigma the Riemann sphere, which I think of as a Riemann surface with its natural complex structure, and then fix an n tuple of marked points. Okay, so m was the rank of the group, and n is the number of marked points, a1 up to an. So they are ordered or labeled, if you prefer. And now I want to consider meromorphic connections. Instead of giving you the general definition, I will be very concrete and consider a setup which, some of you maybe already have, may already know, in particular, if you've heard me talking about this stuff, I don't know, in Geneva or in Zurich. So you consider the V, which is the trivial rank M holomorphic vector bundle over the sphere. And then I want connection which have simple pose at its set A underlined of marked points. So we do the following. You take a complex coordinate Z, and then you consider the complex plane with that coordinate, and then the sphere can always be thought of as a compactification where infinity is added on. Then assume that all the marked points are at finite distance, and denote Ti, their coordinate in this given affine chart. So Ti is Z evaluated at AI. 0 or non-zero, whatever, but a finite complex number. And then I can consider connections like this. So nabla, this star, it's nabla because I am on a globally trivial bundle. It's given by a global meromorphic one form A. And this form I can write as a sum of basically residues, capital lambda I, living in the Lie algebra at these points. And then I want its simple pose, so I divide by Z minus Ti. So this is a meromorphic one form with value in G, defining a logarithmic connection. And I will note here, I will use this later, not right now, that the residue at infinity is well defined, and it's the opposite of the sum of all the residues at finite distance, as you see by taking, the coordinate Z minus 1 and computing just by changing formula for the connection. So all standard stuff. So now I got this, and now I would like to basically consider, as I said in the title, moduli spaces of such. And I will try and do this in the most possible straightforward way. So by describing the quotient, sorry, by describing the moduli space as a quotient instead of giving the abstract definition. So first, note that these connections, logarithmic connections star above, are parameterized by this space m tilde star. The notation is used because, I mean, in some papers you would find this, it's not so important today. This is this direct product, which is just the Lie algebra to the power n, so containing the n tuple of residues, capital lambdas, and then this base space B, which is right now just the space of configuration of n tuples of non-coalescing points in the complex plane. So it's C to the power n minus all the diagonals. I call it B because later on I would like to think of it as the base space of a certain fibration. You will see in a while. So this is the space. And of course, this is not a moduli space, because normally when you do moduli spaces, you want isomorphism classes of objects. In this case, isomorphism classes of connections. So please consider automorphisms of V, right? I want to consider gauge transformations, by which I just mean automorphisms of this trivial vector bundle. Because it's trivial, this should be holomorphic maps from sigma to the group, so they're just constant. This is a simplifying, feature that I have because I am assuming to be working on a holomorphically trivial vector bundle. Otherwise, of course, it's false. So here I just have constant maps, and then the gauge transformation, instead of having the adjoint action and the logarithmic term, it just has the adjoint action here. So there is no time-dependent term, so to speak. So this is the action. If you have A, which is the meromorphic one form defining my connection, I have a new one, G of A, which is just, simultaneous conjugation of all the residues by the gauge element here, which was just a fixed, a fixed one. Of course, this formula is general for any simple, or complex reductively group, if you prefer. For GLN, of course, you just have the conjugation, but this setup, as you can imagine, works more generally. Beware that for other groups, you should not work on vector bundles, but on principal bundles, but then it's the same. And thus, you should say that this action is doing nothing to the marked points. This is only acting on the residues, and the positions are just fixed. So actually, this somehow splits. So I can consider the quotient of the space of residues, and then just add up the product with the space of just positions of times. And this is going now to parameterize not just connections, but isomorphism classes of connections. So connections up to automorphisms of this trivial vector bundle V. So in this space here, right, G to the power n times G by simultaneous adjoint action, which is a quite known singular space. Here I want to think of it as a moduli space of connections. And I would say then that it is a moduli space of connections on the holomorphically trivial holomorphic rank m vector bundles. And I have to say with poles at a certain position. So as the points move, this has a connection of the form above, and that is true for any possible positions of them. That's what I said. You can just multiply by this base space on the right. So you have a family of moduli spaces, if you prefer. That's very well, but right now this is just some space. I would like to have more structure, especially for quantization. So I would like this to be a Poisson or symplectic. And so immediately, what we do is the following. So first I do what I said. So I consider this product, which I denote with a tilde. And so now you have this family of moduli spaces, which you can consider of as a fibration over this base space B. And so now you can have the poles that move. And then I said, I want to have some more structure. So I would like to have Poisson or symplectic structures. To get the Poisson one, that's very easy. You just need to choose an invariant symmetric bilinear formula on the Lie algebra. In this case here, I take the trace. Otherwise, for a semi-simple one, you should take the killing form in general, but here the trace is going to work. Recall that the trace is not the killing form, which is degenerate for GLN, right? So I'm really using something different. And then up to this identification of G with the dual, because it's finite dimensional, so everything works nicely. Now we see that naturally this space here has a Poisson structure, because the dual of a Lie algebra has the natural Poisson Lie, or the Lie in Poisson bracket. And now if you want to go further and to make it symplectic, what you have to do is that you have to restrict to certain symplectic leaves. And here it's totally, explicit in this case. Basically, it's the same as looking for symplectic leaves of G dual, which is taking coadjoint orbits. And here we will do the same, only that we will have products of coadjoint orbits. So let's assume that all my residues actually live, they are constraints to live in a given adjoint or coadjoint orbits inside G. I can say adjoint or coadjoint freely because I have this identification, which is given by a G invariant transformations. So I can turn every adjoint orbit in a coadjoint one. And it is known that coadjoint ones, so this is the most intrinsic way to think about it, coadjoint orbits are Hamiltonian spaces for the action of the Lie group, by which I mean that they are symplectic manifolds endowed with an Hamiltonian action. The symplectic structure is the KKS one. This is the Kirillov constant Souriau symplectic structure, which I'm not going to, write any formula about. So this is something that I take as standard. And then the moment map is just the inclusion. So you have for each I the inclusion of each orbit in the dual Lie algebra. And so this is actually a moment map for the Hamiltonian action. That's a very standard statement in symplectic reductions. So I denote O underlined the collection of these orbits. Every time that you see something underlined, it means that it is a collection over all the mark points. And now I think you agree that I have this proposition. Basically, I walked you through the proof of this proposition up to some technical details. So you can consider the symplectic reduction of this product of coadjoint orbits at level 0. This is also called, to be totally explicit, the Marsden-Weinstein symplectic reduction of this space there. And then you should see that this is, this gives an explicit realization of what? Of a moduli space of logarithmic connection on that trivial rank n holomorphic vector bundle with poles at these mark points, and moreover with residues restricted to live in this collection of orbits. The last piece of the proof I write down, note that here in the parentheses, I wrote that I have a holomorphic symplectic moduli space. So beware that because I have a complex group, my KKS symplectic structure is not a real structure. It is a holomorphic symplectic structure with respect to the complex structure of the Lie algebra. And so this is actually a holomorphic symplectic manifold. Right now, I am not making any choice of the orbits. You could ask which orbits are you taking. I am just going to say something more about that when I want to talk about quantization. But here I can make this general statement. As I said, there is something missing from the proof. I passed some details, but the proof is just this tautological fact that the vanishing of the sum of the moment maps for each inclusion, which is exactly the moment map on this product. So this should be the Hamiltonian sums, in the Hamiltonian category. So the vanishing of the sum of these moment maps is precisely imposing that the sum of the residues is 0. And I told you above that these sums, or rather the opposite, was the residue at infinity. So actually asking that I am considering the level 0 symplectic reduction is precisely like asking that I have connections which have no pole at infinity. So that's essentially how one sees that this works. In general, I will just say this. I don't think I will have time to say more about that, but this is actually also possible to generalize in the irregular case. So also with high order poles. I mean that one can make sense of moduli spaces of connections with higher order poles at mark points and prescribed residue orbits. And then it is still true that this can be realized as a certain holomorphic symplectic quotient of a product of orbits. only that now these orbits will be somehow more general than what I have here. So this description is actually generalizing in a straightforward manner to the irregular case. Okay. And now, that I have said that, now recall, before I said that I want to have a space which has more structure, it's symplectic, but now you will recall that actually I had a fibration of such spaces over this space B of configuration of the simple pose. So you have a fibration of moduli spaces, which is now, thanks to this proposition, a symplectic fibration. So a fibration of symplectic manifolds. And so now I want to state this. First, that we have a symplectic fibration over this space B. But actually that more is true. So actually this is a fibration which is naturally equipped with a flat connection. So normally when you have a vector bundle, a connection or a causal connection is, a differential operator acting on sections. You can think of it in several different ways, but you can do the same in the nonlinear case. There is a more general notion of connection which encompasses that for vector bundles and for principal bundles, which is a Hare-Hessman connection. And so what I'm saying is that here there is a natural flat or integrable Hare-Hessman connection, which is moreover symplectic. This just means that if you integrate the connection along small paths, so if you consider the parallel transport or the holonomy, this will integrate to symplectomorphisms of each fiber. And this natural flat connection is called the isomonodromy connection. So this is something which you also get canonically from this setup. You don't just have a fibration, you have a flat symplectic fibration. So this is called a local system of symplectic manifolds. This is, I think, something that it's not so well, it's not a viewpoint that it's not understood, but known somehow. So people think about this fibration when talking about isomonodromy in a very concrete way with equations, for the isomonodromy equations or the Hamiltonian systems and so on. But abstractly, it is very good to think of it as local systems over certain base spaces, because again, this is a natural geometric viewpoint which generalizes to higher order poles. So that's actually a very somehow unifying, powerful geometric viewpoint. And note that you are paying a price here because you basically don't see any formula right now. This is very abstract. But what you gain from this intrinsic approach is that this is better suited to consider quantization. So that's why I like this very much, because if you state things in this way, the quantization comes out more naturally than if you have made a lot of local choices. Okay. Very well. So if you followed so far, I argued that somehow having logarithmic connection with varying poles gives us a local system of holomorphic symplectic manifolds. That's somehow the punchline. And now I would like to say just a few words about this isomonodromy connection and then quantize it. So how is this connection defined? Just a few ideas. So note that because I had meromorphic connection with poles there, I can very well remove the poles. So consider this open Riemann surface. And then the connection will be holomorphic there, tautologically. But a holomorphic connection on a Riemann surface is flat for dimension reasons. And so you just have a flat connection and you can take its monodromy representation. You always have this canonically attached to the connection. So you naturally have this holonomy or monodromy data that I denote nu of nabla. This is supposed to be the Greek letter nu, which is, as you know, a representation of the fundamental group of the open sphere at some base point with values in G. Because of course you will get automorphism of the fibers which are c to the power m, and so an element of GLM, the group. And then what I am somehow skipping over, because I would like to say something more about quantization, is that actually this map actually extends to a fiber-wise map. So I had the families of such moduli spaces of connections, and then I can take each of those and consider this map that gives, that gives me the monodromy of the associated holomorphic connection. And this will define for you a map of vibrations. So nu, from this vibration I described for you just a few minutes ago, to a new vibration here that I denote m tilde b, whose fiber over a choice of Mach points is precisely the space of representations of the fundamental group, but taken up to conjugation. So this is the actual monodromy data. It's this representation up to a conjugation. So first remark, don't care too much again about the notation. The R stands for de Rham and B stands for Betti. So this is related to what's called the non-abelian Hodge theory on the curve, which I need, we don't need at all right now. But again, this is the names by which these objects are known somehow in the literature. So that's why I'm using it. And second remark, it's not quite true that I get the whole of the space of homomorphism. You will see that here I have an inclusion, because there is basically the following fact, saying that I want to have residues in fixed orbits and them summing to zero on the side of representation spaces amounts of saying that the monodromy matrix you get will be in prescribed conjugacy classes of G. So the orbit is somehow integrated to a conjugacy class. And the fact that the sum of the residues was zero gets translated into the fact that the product of these matrices is equal to 1 instead inside the group. So this is, you should think of as the exponentiated version of this one. More formally, this is called the Riemann-Hilbert correspondence, whatever the name. And for those who know the work of, Anton, Alexiev, and then Melkin and Meinranken from 2002, I believe that's an example of a quasi-Hamiltonian reduction, this space on the right, this space of representations. No need to use any of this, but it's still there. Okay, today I'm concentrating on the side of the connections. So now that I told you that there is this vibration map, I will just add that I can now define a connection on this space, on this vibration here on the left, just by saying that I want that the monodromy data are locally constant. So as you deform your connection, so as you vary the positions of the points, you will move around in this map here and getting different representations. You can ask that these are locally constant, and this will define for you this connection on the left-hand side. That's why it's called the isomonodromy connection, because it is obtained by requiring that the monodromy is locally constant as you move through the formation. So you should imagine that you have something like B, and then fibers, each of those is a different space in correspondence of some choice of Mach points, and then essentially we have some leaves inside this vibration cutting horizontally, which are precisely defined by saying that if you take this map here, the monodromy along these leaves, locally around the point you find some constant element of this space here. So the monodromy data are fixed, and this defines some leaves, which gives you an integrable Hellesman connection. As I said, this is very abstract, but it's very useful if you want to generalize it and quantize it. So that's why we make this, this effort. Okay, so second punchline, giving logarithmic connection is the same as giving a local system of symplectic manifold, and this flat connection is obtained by requiring that monodromy data are locally constant. This viewpoint is originally due to Hitchin. There is a paper of his in Notes on Frobenius manifold, something in honor of Boris Dubrovin, where he explains about this symplectic interpretations of isomonodromic deformation. And now we want to quantize it. So now we replace this by a projectively flat vector bundle. This is the idea. The classical stuff was a vibration of symplectic manifold. The quantum one will be a family of vector spaces, so a vector bundles, also equipped with the flat connections. And to construct them, we use conformal blocks. So that's where conformal field theory and conformal blocks arise in this story as a quantization of this local system of manifolds. This is actually the main point I would like you to bring home somehow, that there is this picture having local vibration and which gets quantized to vector bundles with flat connections, which is the good viewpoint for quantization and which applies much more generally. In particular, there is also a viewpoint in this using geometric quantization, but I will not discuss this today. So now, for the time I have left, I would like to say something about how I construct this conformal block bundle, some background stuff, and then again, let's see if I can spend a few words on the generalization. Small remark before doing this KZ, there is actually a natural way to have the quantization. So the isomonodromy connection, IMD for short, is given by a certain non-autonomous Hamiltonian system. I thought I wrote you this here so that at least you see some equation and this is not totally abstract. So if you write these Hamiltonians here, complex maps taking the residues and the positions of the points as inputs and giving you a complex number by these traces here. This is called the Schlesinger system. This is what controls the isomonodromic deformations. So this is what defines these connections above. But then there is this very straightforward way to quantize it, which is saying restrict this function to a fiber. And now you actually get an algebraic function from G to the N to C. So an element of this space here, the symmetric algebra of the dual of G to the power N, I would need a new parenthesis here, but up to my identifications, this is just the same as the tensor power of the symmetric algebra of G. And now, basically, the direct way to try and quantize this is to construct quantum Hamiltonians, which are functions taking value no longer in the symmetric algebra, but in the universal enveloping algebra, tensor power with N. There is one way to do this, which is totally straightforward. And so this gets you a quantization of the Schlesinger system, and you get KZ. This was first somehow understood by Reshetikhin back in 1992. And John Harnad in 1994. But instead of showing you this, I will go to the conformal block bundle, which is more complicated, but which is somehow the conceptually better approach, because there you see the conformal symmetries appearing. So now for KZ, okay? So now I would like to recall something about this KZ connection. Right, so assume now something more on the orbit. Let's assume that these orbits OI are actually semi-simple. So they are the orbits of some diagonal element. So I mean that they are the orbits of a certain element, small lambda I, which lives in the dual of the standard Cartan subalgebras, the standard Cartan subalgebra of diagonal matrices. Again, for any other simple algebra, you would generalize this taking other Cartan as you want. And now this is the first fact I want to recall. There is a pairing. So if you take the loop algebra, which is this tensor product, so this is like G-valued formal Laurent series in one variable. Then if you have a meromorphic form with value in G and just a meromorphic function, you can just take the trace and the residue to get a pairing, as I write here. And so this is non-degenerate, and this provides you a duality which sends my elements that I had before, this residues over Z minus Ti, to just this dual weights lambda i's defining the orbits. So I have no more time to explain this idea to you, but I would just like to stress that this is telling us what we should do for the quantization. So to quantize orbits of these elements here, which are related to this, I can just take weights and trying to defining vector spaces out of modules for the Lie algebra, depending on this choice of weights. That's the way in which this quantization should work. You should match up your residues and then the product of their orbits, which gives the moduli spaces with these weights. And then to get to some linear object, you can use modules defined by these weights to go to the quantization. This is exactly what Verma modules do for you, and which I will say something more about right now. And this is why I was talking about Verma modules in my abstract. Right. So let's have a very short background on Verma modules. So recall that This loop algebra has a central extension. So as a vector space, it's the loop algebra plus some element, capital K, and then there is a non-trivial bracket, which is essentially defined by this cocycle here. So this is called the affine Lie algebra. And what we do is that we will have modules both for G, so the finite dimensional one, and for the affine one. These finite Verma modules and affine Verma modules. How do you do? So there is this standard setup. So let me go quickly through this. You choose you consider the root system for your algebra with respect to the given split Cartan. And then a positive root system within that. Then you consider the standard triangular decomposition where you have the Cartan and then two nilpotent subalgebras. These are the sums over positive and negative roots of the spaces G alpha, which in turn are the weight spaces for the adjoint action of the Cartan on G itself. These are one-dimensional spaces because we are on a, in finite dimensional case over an algebraically closed field. And then you consider the positive Borel subalgebra associated with all that, which is just the Cartan plus the positive nilpotent. In the case of GLN, this is just saying that n plus and n minus are the spaces of strictly triangular upper and lower matrices. T is the diagonal one, and then B plus is a space of upper triangular, not necessarily strict. So you can have something not zero on the diagonal. And then you generalize to other root systems. Then there is a very basic proposition, which I will not prove, it's just a lemma. The commutator Lie algebra of B plus with B plus is n plus. So you get this nilpotent as do the commutator. And so the abelianization, so this algebra mod, the ideal generated by the Lie bracket is just T canonically. So giving a character of B plus of this Borel is just the same as giving a linear function on T. And then if you give me one, then I can induce a representation. So you can take the module, the one-dimensional module defined by lambda, down here, C lambda, and you can just tensor over B plus with UG. So this is a very standard construction representation theory. This is just the left-induced G module starting from this B plus module. And this is called the Verma module with that weight. More concretely, I mean, this is generated over n minus freely, so with no relations over n minus, generated by one vector, which is a highest weight vector. So it's killed by n plus, and it's acted on the Cartan via the given weight. So this is, I hope, something you've seen in the past. This is used to, to get with certain choices of weights, the reducible representations of the algebra, and then taking dominant integral ones, the finite dimensional representations, and so on. So this is the finite Verma module. And then it's just the same for the affine one. Let me not spend too much notation of this. So now you define affine Verma modules where you do the same for the affine one. So I will define an analogous Cartan T hat and a positive Borel B hat plus, such that now giving a character of this is the same as giving a pair, so an element in the dual Cartan, and then something in the dual of this new central element. So because this is just a line, giving an element in the dual is just the same as giving a complex number kappa. So if you give me this number and another element lambda as before, you get this module here, which is now a module for the affine Lie algebra, and which is called the affine Verma module. Kappa is the level, right? For those of you who know CFT, this is just the level in the WZW model. That's exactly how it arises. It's related to the central charge in the Liouville model, and I mean, all this stuff that we do not need today. So I have these two very well, and now let's move on. So recall that I wanted to consider mark points. So please take again the mark points I had before, this A underlined, and then I want you to consider G-valued rational functions with poles there, these objects here. This is naturally a Lie algebra just by taking the constant bracket on the target space, on G. And moreover, I denote it's G of A underlined because it depends on these two, nothing else. And you should see that I can take Laurent expansion at each pole, at each mark point AI in this set. This is a map tau I, which gives me an element of the loop algebra. If you think of the loop algebra as you know, power series in a complex variable which vanishes at the mark point. You can always do this. You can just take a new local complex variable. I choose one which vanishes at the pole. By definition, this one will work. Recall by definition that the I is by definition Z of AI. So tautologically, this vanishes there. And now you have these Laurent expansions. And thus, I can do the following. I can take the tensor product of all these Verma modules. And then I have a natural map from these rational functions to endomorphism of this tensor product, which is just taking a function and giving me the sum of each Laurent development, each of these acting in a different slot of the tensor product. So I develop at the first pole and I act on the first slot, plus second pole, second slot, and so on. And this is a natural action, but moreover, proposition and sketch of proof, this is actually an action as Lie algebra. So this is not just a mapping to the space of endomorphism, it is actually a morphism of Lie algebra, where of course this is endowed with the commutator as a Lie bracket. And the proof, which I do not do, is a straightforward computation based on this elementary fact that if you sum all the residues of any meromorphic one form on the sphere, you just get 0. So this is essentially, if you try and write down what it means, you will have two commutators. One of these two commutators will have more terms, which will be killed precisely of this fact here. So you have a natural Lie algebra action of rational functions on this tensor product. And thus I give you this definition, which is the definition of WZW model, conformal blocks, sorry. So WZW stands for West-Zumino-Witten, but sometimes this is also called the West-Zumino-Novikov-Witten model, just terminology. We are in genus 0 because it's on the sphere, and we have these conformal blocks using Verma modules. So this gives me a vector bundle over the base space of configuration of points, and each fiber is precisely this quotient here. So I have this space here, which is acted on by the Lie algebra, and I kill all the vectors in the image for these actions. This is called the space of coinvariance. So whenever you have a Lie algebra module, if you take the Lie algebra mod, the action, you know, the image of all these elements here, this is the space of coinvariance. I wrote here with a caveat, beware of other versions, because there are other versions of conformal blocks. That's the one I want to consider today, but sometimes people take dual modules with, invariance instead of coinvariance. And sometimes they do not take Verma modules, but integrable highest weight modules instead. But for today, this is enough. So there is a proposition, which I will not prove, that taking actually this space here, so the coinvariance for this action of this huge space of conformal symmetries, is the same as taking the tensor product of the finite modules mod out by constant functions, so just elements of G. And this for any point, this is totally canonical and independent on the choice of points. So this is another model for the space of conformal blocks that I'm giving you. And now what I want to do is that I want a flat connection on this bundle. Recall that I want to quantize my local system by giving you a projectively flat vector bundle. So I want to define a flat connection there. And the idea for doing this intrinsically is that I will define a connection acting on this tensor product. So I will define actually a canonical flat connection on the trivial vector bundle with this fiber. And then I will show that this is invariant by the action of these Lie algebras. So there is going to be an induced or a reduced connection, if you prefer, that it's still going to be flat, and this is exactly KZ. Very well, so now I will give you just ideas for this. So the Virasoro algebra actually acts on these affine Verma modules by the Sugawara operators. So I just need L-1. In brief, you consider infinite sums as follows. So you have some denominator with the level and the dual Coxeter number. And then you have this infinite sum where here you go over a sum over B, so an orthonormal basis for the trace. And then you have the normal order product where you have X tensor Z to the minus J, and then X tensor Z to the J minus 1. And then you normal order this, which just means that you put the positive exponent of Z, the positive degree, to the right. So these are called the Sugawara operators. L-1 in particular is this, but there is one for each integer. And then, so there is this basic fact that you can read in Victor Katz's book about infinite dimensional algebras, that the adjoint action of this L-1 on the affine algebra, it's actually basically the opposite of the derivative. This is like, you know, if I was deriving this rational function with a minus. So this is just basically either a hard computation or some more conceptual proof. And as a corollary, I can consider this connection here, which is flat, where I take all these Sugawara operators acting on the ith slot. And this is going to be flat here, but moreover, importantly, the corollary is not that this is flat, this is automatic. What is non-trivial is that this is going to be invariant for this rational function action above. So this fact here implies this fact there, so that you have an invariant flat connection for these rational functions. And so we get a reduced connection on the bundle of conformal blocks, which is exactly the Casey connection, i.e. the Knizhnik-Zamolodchikov connection. This, recall, that was first introduced in 1984 by Knizhnik and Zamolodchikov as, you know, equations satisfied by correlators in this conformal field theory model in dimension 2, but mathematically it's exactly a flat connection on a vector bundle. It's constructed like this. And to give you something, yes?
Sorry, just to let you know, you still have 5 minutes.
Thank you very much, yes. So exactly, now I'm closing this stuff here, and then I will say 2 words about the irregular stuff and I'm done, thank you. So explicitly, this is the way in which this is written. So this is quite long. So because it's a connection from a trivial vector bundle above, I can write it as the differential, the RAM minus a1 form. This form is given by certain quantum Hamiltonians if I develop it, you know, if I expand it in the given variables. And this is the actual formula for that. So you see the same denominator. Now that I see this, I recall that there is a mistake here. There should be a 2 here. It's not very important, but there should be a 1/2 in the Sugawara operator, whatever. Then you see that here the 2 vanished. And here you get this element here, omega ij. So omega ij is the action of a certain quadratic tensor on the ith and the jth slot. And this is called the canonical quadratic tensor of this quadratically algebra, which is just the tensor products of, you know, elements of this basis I've chosen. This is actually independent of the basis. And so you get these Hamiltonians here, the Casey Hamiltonians. You should compare them with the Schlesinger Hamiltonians above. Now, you cannot if I don't write them again, but you should recall that the Hamiltonians I had above were like hi equal a sum for j different from I of traces of the residues divided by ti minus tj. So this makes it clearer why I said that this is a quantization of that. Somehow this function, an element of the symmetric algebra, gets quantized to this element here, you know, whose class lives in the universal enveloping algebra. So in the time left, so I just have 2 minutes for this, but that's, I mean, that's okay. I would just like to say very shortly 2 words about how we went about to generalize this to irregular poles, which is, as you can imagine, I mean, more technical, but now you see how these ideas worked in the standard case, and I would just like to give you the very major ingredients to extend this to higher order poles. So this you can read in this paper with Giovanni that was online just December of last year. So as I said, the main point is that we want modules for G hat. I want to generalize Verma modules. I will just say the following. I will say that before I had something induced from a positive Borel subalgebra here, and that somehow characters of this B hat plus were related to weights in some Cartan subalgebra. First fact. And second fact, the weight was related then by this duality that I told you above, related to something like lambda over z dz, which was an element in, you know, a meromorphic 1 form with a simple pole with values in the Cartan. So these are the steps. I had some subalgebra whose scatters are given by something in the dual of a Cartan, and in turn, this dual of a Cartan was given by a residue. So what we did is the following, is that we consider the new subalgebra, which we denoted sigma p, still inside the, sorry, this is still the affine, there, such that essentially characters are identified with elements of the form some lambda into dual, and then an n-tuple of elements tau1 up to tp minus 1, where p is just an integer, which live in this direct sum here. So t tensor z to the I dual. So we don't just have element in t z to the power 0 dual, but positive powers of this. And this is exactly what we wanted to do, because with the previous duality, so with previous duality, then these elements here, these pairs lambda and tau underlined, is actually mapped to something of the form lambda over z dz plus some other term, namely the differential of a meromorphic form, which now carries higher order poles. So Q is something like sum for I from 1 to p minus 1 of ti divided by z to the power I. So these new elements here are duals to this tau here, just as this element small lambda here was dual to this capital lambda that we had there. And now induced, so the main idea is to induce again. So you get this that we called singularity modules associated to all this data here, which are just the induced modules from this new algebra sigma p to the affine algebra by using all this data. So this bigger choice of characters related to this connection with an irregular type, and still with a given level. And then same as above, I will just say this. Same as above means that you do the tensor products of this here, where now you can allow for whatever order of poles you want. So you have several of these choices and several of these poles here. And then you show that these assemble into a flat vector bundle over B. And the flat connection is still obtained using the Sugawara operator. So use Sugawara. And this action of rational functions. So we get in this way a generalization of the KZ connection, which gives a representation of something that was first considered by Reshetikin. So we have a representation of that and an extension of the Reshetikin connection. And this is somehow related to, as I said, via this duality, to connections on the sphere, on the trivial bundle, which have higher order poles. And the new parameters are these meromorphic functions here, complementing the residues. So I will stop here. I guess I'm already up. Sorry, time's up. Thank you very much.
Well, listening. Thank you very much. So let's thank Gabriele for this very nice talk. Yes, questions from the audience. We have one question from Nima.
Yes.
Thank you very much. It was a great talk. So one question is, so you start everything with a Riemann sphere, right?
Yes.
So is there any higher genus extension, let's say?
So yeah, absolutely. So basically here I took the genus of sigma to be 0, and I discuss everything for G equal GLN. So you could ask questions about, can you move sigma, so having higher genus, and can you also change the group somehow? These are the first two parameters you can have. So you asked about this, and here I must say that you touched the most delicate point, because the higher genus extension is very, very complicated in the quantum case, as far as I understand, for one main reason, is that here, if I told you I considered a simplification assumption, I assume that my vector bundle V was the trivial one, right? So this makes it possible to have this constant space of gauge transform and other simplifications. the advantage in genus 0 is that if you consider this moduli space of connections on trivial bundle, which is contained in the moduli space of all connections, now you understand why there was a star. So if I take connections on any vector bundle, not trivial, this is open in genus 0. So this is an approximation to the actual moduli space you want to study and to quantize, and that's why it is interesting to see it. So geometrically, for instance, this here is known to have hyperkähler metrics, and those were studied on these open parts in the classical case. And so that's why the quantization is still somehow relevant and important. First fact. And second fact, this has this nice description as a reduction of orbits, right? So as quotient of orbits. Or I should say as a product of orbits. But this here is false. So you don't have this description as a product of orbits, and so it's worse. And now if I go in genus 1 or more, you still have this inclusion, but this is no longer open. That's what breaks in higher genus. So the description here fails, and this now in higher genus, this has positive codimension. So most of the stuff I was doing here is breaking down, and so new ideas are required somehow. However, I can say that there are flat connections in the WZ and W model for higher genus. So the WZW connection exists even in higher genus. Then it's just it's not just KZ anymore. And so somehow it is known that the semi-classical limit of this connection is equal to the isomonodromy connection. But the other way around, the quantization is what is really more complicated.
So the thing is that, yeah, you're talking about this isomonodromic connection or whatever. I mean, so if there is like this more general thing, then I don't know, like the connection to, like, for example, Kontsevich integral or something like this is something that might be interesting in this setting, right?
I don't know. So Kontsevich integrals, what do you mean more precisely? I don't quite say, sorry.
Well, when you look at basically the monodromy of the KZ equation, of the KZ
but that's for me. So for me, that's independent of quantization. So once you quantized it, you have a flat connection, and then you can take the monodromy. I agree. So here in particular, I would have KZ on this bundle here. Because it's flat, you have the monodromy, so you get an action of the fundamental group of the base by monodromy. So on this space of conformal blocks, and this was used in the Konod-Riemann theorem. So this is somehow saying that the monodromy of KZ is related to the universal quantum R matrix of the Jimbo-Drinfeld quantum group. I think that's the statement. So after quantization, you can look at that monodromy. And so, yeah, I think the question is open. I mean, as to, I don't know how much of that is settled in higher genus, but I do know that the question is open if you still are in genus 0 and if you consider higher order poles. So I can do the same as I told you for this new connection that we had with Giovanni. And I think it is an open question to compute the monodromy to somehow generalize this, this business here. So this is, I think, an open problem.
Thank you very much.
Okay, I think we have time for one more quick question. So maybe then I might ask more.
Wait, I think that Jan wants to ask a question, but he physically raises his hands.
Oh, okay, very good.
I like it. Go.
Wait, Jan, I need to ask you to unmute.
Hello.
Hi.
Hi. So, sorry, maybe it's kind of like a question in the same direction as Nimas, but you know, there is this quasi story where you put some marked points on them, or like you mark parts of the boundary. And when so the question is whether you know something about this, and why I'm asking is that for surfaces with boundary, all those bundles are trivial. So.
But so for me, the quasi stuff would mean to consider, I mean, I think you're referring to considering the quasi-Hamiltonian reduction to get the representation space, or what do you mean?
Yeah, so what I mean is that maybe it is easier to work with everything in terms of this quasi-Poisson, or
so
like quantizing this with some kind of.
Right. So, I mean, I know of work in that direction. So you would take the quasi-Hamiltonian spaces that you get of this quasi-Hamiltonian reduction of not the orbits, but the conjugacy classes. But for me, it's not so clear that it is simpler, because then, I mean, the quantization, instead of just giving you, in this simple case, the universal enveloping algebras, you get, you know, you are also deforming the co-product in that case there, essentially, because you have, you know, group valued moment maps, as you know, and not the algebra one. So basically, I think this is related to passing from this here, which is actually called the classical KZ connection. What I talked to you about is actually called the classical KZ. It is a quantization because you go from sim G to UG, but now this is co-commutative, and you can then go to the Jimbo-Drinfeld, you know, UQ.
Mm-hmm.
And so I think there is a way to interpret this here as a quantization of what you're saying. So of the Betti space, I would call it, of the, you know, quasi-Poisson or quasi-Hamiltonian reduction there. And so somehow this is a further deformation of the classical connection, as far as I understand. So I actually had this question that, I mean, I'm not sure how much in general this has been done, of considering quantum quasi-Hamiltonian reduction instead of quantum Hamiltonian reduction, to try and quantize the character varieties on that side there. Mm-hmm. And there are works there. I mean, I know for sure this is not a new question by any mean, but
there is this recent paper by Safronov, for example, on quantum moment maps.
Quantum quasi moment map.
No, just quantum moment maps. But I think his setup is general enough to also include this, because like on this he was categorical, and there is just these correspond to those Drinfeld categories.
I see. Yeah, exactly. The point should be that you should need the associate. Yeah. Okay. Very well. Then,
maybe we can talk about this in the.
Sure. Then you will explain to me
in this computer game.
Okay. Yes.
Okay.
Thank you very much.
Well, so then let me take up on this idea and just transfer all the further discussions into the discussion session. So first of all, let's thank the speaker again. So thank you. And let me stop the recording.